So this was the problem I asked you to work on. So let's just work through, and irrespective of where you got, it doesn't matter. You're not graded on how far you got in these problems. This is just an attempt to try and give you time to do what I would normally do in the regular classroom, which would be to work through some of these problems and then model the solutions. So problem statement that you've been working on, you've got water that's treated before being discharged into a lagoon. You're told the volume of the lagoon, you're told the flow rate, and you're told that it's been operating and it's now operating at steady state conditions. So let's work through this. So we have a lagoon. That's me right. Okay. So here's our lagoon. And it has a volume of 5,200 cubic meters. You're told that the wastewater is flowing in with a flow rate of 0.15 meters per second. Okay. And you're told that at steady state, the concentration of the lagoon is 250 milligrams per liter. Now, in order for that volume to be constant, then the flow out has to equal the flow in, so it's 0.015 cubic meters per second. Since we have a CSTR, we will assume we have a CSTR, then the concentration in the lagoon is equal the concentration leaving. So we've got a well-mixed system. We'll assume that there are no dead ends in the system. It's an ideal, completely mixed reactor, so an ideal CSTR. So that means that the concentration leaving is also 250 milligrams per liter. The salt is conservative. There's no decay. Now we want to draw the system boundary, and this is the system boundary is simply around the lagoon. It's not around the rest of we don't care about what happens in the rest of the wastewater treatment plant. All we care about is the lagoon. The next thing you're asked to do is to write a mass balance in words. So we've stated our assumptions in writing this out. And now we want to write a mass balance in words. So the mass balance in words, simply the change in mass with respect to time is equal to the mass rate in minus the mass rate out minus the mass rate decayed. Okay. If we were looking at a chemical that was actually reacting and forming in this reactor, then the last term would be positive because it's forming. We're told that we have steady state conditions. So if we have steady state conditions, the change in mass with respect to time is equal to what? Zero, exactly. Okay. and we have mass rate in minus the mass rate out. And we said that the chemical is conservative, which means K, the rate constant, is equal to 0. So this is also 0. So that means in this case here, mass rate in is equal to mass rate out. Okay, so at steady state, 250 milligrams per liter. Okay. The concentration then suddenly suddenly increases to 1,000. So we're going to plot concentration as a function of time. Okay. So time 0 is when it suddenly decreases. If that's the case, then the concentration at time 0 is equal to, and we're looking at the concentration in the lagoon or the concentration leaving. We have a CSTR. So at time 0, the concentration in the lagoon is equal to what? It's 250. Exactly. And the concentration at steady state is equal to what? So once concentration in now is equal to 1,000. So at steady state, the concentration, okay. So we've increased Cn to 1,000. Okay, exactly. It's going to be 1,000. So somewhere out here, it's 1,000. And the concentration is going to increase exponentially until it reaches 1,000. The equation that we can use is that the concentration at any time is equal to the concentration entering 1 minus E to the minus Q over V times T plus C sub naught E to the minus Q over V times T. Okay. So this is the equation that we would use right here. This is what the plot looks like. Okay. Now, okay, how do we know that there was an out from the lagoon based on the problem statement? Good question. Okay. The problem statement says that the volume of the lagoon is 5,200 meters cubed. If there isn't an outflow, what's going to happen to that volume over time? Think about your bathtub. Okay, you're filling up to the bathtub. If you have the stopper in the bathtub and the drain, exactly, the volume's going to increase. Okay, so in order for that volume to be constant, and anytime you're given a problem where the volume is constant, the flow rate in has to equal the flow rate out. Otherwise, the volume's increasing. Problems that we do in the class will be relatively straightforward. You can always assume, if you're told that the volume is constant, always assume that Q in is equal to Q out. Okay. We only have about 3 minutes, so we'll process this together, okay? So the plant operators restore operation to the plant. So they bring the concentration back down to 200 milligrams per liter. So same problem. The only difference is now we're starting at 1,000 milligrams per liter in the lagoon. Bring the plant back to operation, proper operation, and now Cn is now equal to 250 milligrams per liter. At steady state, what is the concentration in the lagoon? 250, exactly. So if we plot concentration in the lagoon as a function of time, we're going to start at 1,000. We're going to end at steady state at 250, sorry, right there. So the concentration is going to decrease exponentially. Same equation applies. The exact same equation. The only difference is if we go back to this equation here, now C sub 0 is 1,000 and C sub n is 250. And the graph looks like this, the blue line. We're not going to get to the other problems. What I think I may do, I've recorded this. I will post this problem on Lon Kappa. Okay. I will, on Wednesday, I'm going to have Wednesday's group work on the next problem so that by the end of the week, we'll have 3 different solutions, but the 3 different problems here. So that you can go back, you can look at what I've done here in terms of the recording, but you can also look at what Wednesday's group did with the next problem, and then what Friday's group did with the last problem. Does that make sense? I'm finding my way on this too, because this is the very first time I've ever done this kind of this model with the flipped classroom. But I wanted to make sure that you have the opportunity to work together.